Today's lecture is on the topic of nonparametric estimation. Roughly speaking, nonparametric methods refer to methods for models which are not parametric. So, what does that mean? Let's consider a setting where an outcome of interest, this is a y, is distributed according to some cumulative distribution function, f naught. Recall here that the CDF is defined as the probability that y is no more than some value lowercase y as we trace out this lowercase y. Now by our model for f naught, we mean the postulate that f naught belongs to some family, this calligraphic f, of candidate distributions or candidate CDFs, f. In the case where this family of candidate distributions is indexed by some index theta, belonging to a subset, capital theta, of a finite dimensional space. That is, this d, denoting the dimension, is a finite number. When that happens, that is, when our model takes this form, we refer to the model as being parametric, or P for short. As a specific case of a parametric model, we can go back to our introductory statistics and probability classes, in which case we typically take y to be normally distributed with some mean u and some variance sigma squared. So in this case, capital theta, our index set or parameter space, is two-dimensional. When the model is not parametric, that is, when this index set does not belong to a finite dimensional space, the model must be inherently infinite dimensional. And that's what we mean by a nonparametric model. That is, a model where the family of candidate distribution cannot be viewed as being indexed by a finite dimensional set. As an example of such a family, we could think about this family, calligraphic f, which contains all of the functions or CDFs which not only map into the unit segment, but which are also continuous. Now, the property of continuity cannot be phrased in terms of a finite dimensional parameter, so this space here, or this family, is inherently infinite dimensional. Now, thus far, our discussion concerns a model, or a model for the distribution of y alone, but typically we're interested in not the marginal distribution of an outcome, but the distribution of some outcome of interest conditional on other variables, say x. That is, we're interested in modeling the conditional distribution of y given some regressors, x. Whenever we're interested in this set, or whenever our interest lies in this conditional distribution, or perhaps just features of this conditional distribution, we're talking about a regression setting. Again, a typical regression model that you may have encountered in an earlier econometrics course states that y is conditional on x normally distributed with a mean which is, say, linear in x and some constant variance sigma squared. It could also be that we're just formulating a model for the conditional mean of y given x. For example, that it is linear in x as well as parameters. In this case, we're only modeling a particular feature of the conditional distribution of y given x, namely the mean. Now, often our model or regression model has both parametric as well as nonparametric parts. And when this happens, the model is known to be, or referred to as, semi-parametric, or SP for short. going back to our mean regression model, where we're formulating a linear model for the conditional mean of y given x. Since we are only formulating a parametric model for the mean, that is one feature of the conditional distribution of y given x, the model is semi-parametric. For example, in only specifying a model for the mean, we're leaving the conditional variance of y given x to be just some function of x, that is, some nonparametric element. So strictly speaking, in our earlier discussion of the linear model for the conditional mean, we were dealing with a semi-parametric model. Now, in today's lecture, or the topic for today's lecture, is to instead give nonparametric approaches, to consider nonparametric approaches to modeling the conditional mean, and develop estimation methods for such nonparametric approaches. So, for today's lecture, our object of interest lies in the conditional expectation of y, viewed as a function of the conditioning variable. As already mentioned, we've earlier dealt with models that were linear in the parameters, where we formulated a linear model for this conditional mean. And we've also seen examples of nonlinear regression models. For example, when the outcome is known to be non-negative, it may make sense to formulate an exponential regression model. Or if the outcome lies between 0 and 1, for example, when it's binary, it may make sense to formulate, say, a logistic regression model. Of course, these specifications, these parametric specifications, beg the question, what happens if this choice, or choice for the functional form of these conditional expectations, what if these functional forms are not correct? That is, what if our parametric model is misspecified? And as a follow-up, is there any way to avoid specification error altogether? The answer to this is, well, somewhat. That is, we can never truly hope to avoid specification error. That is, we can never hope to avoid specification error altogether, but we may limit specification error by using nonparametric estimation methods. Okay. So having given this introduction, the rest of the talk now aims exactly for this goal. That is, we'll develop various nonparametric estimation methods, focusing on what's known as kernel methods. So we'll start out by introducing the kernel estimator, also known as the Nadaraya-Watson estimator, and then we'll look at a close cousin thereof, known as the local linear estimation method. Finally, I'll end the talk by a discussion of the problem which is often referred to as the curse of dimensionality, which applies to all nonparametric estimation methods, not only the kernel methods considered in this video. Alright, so starting out with kernel estimation. So let's look at a couple of graphs to fix ideas. So here I've simulated data on a scalar x as well as a scalar y. And I've drawn 100 data points and scattered them in this picture. Now suppose that we were given a data set containing these 100 points, and we were asked to, for whatever reason, estimate the conditional mean of y at a particular point of x, say point 15, so here, or something like that. Now, a natural way of proceeding would be to say, oh, let me just identify or locate the outcomes for the observations, or i's, which had x equal to 0.15. And let me then, since I'm looking for the conditional mean, let me just average over such y's or such outcomes. Now, while this idea, based on the analogy principle, seems intuitively to be a good idea, if we were to zoom in on this picture, if I had a zooming device, I would zoom in at this point. But if we were to zoom in on this picture, it would become apparent that at point 15, there are actually no observations. So if we try to construct this average, we would run into trouble immediately. Now, while this idea based on the analogy principle seems like it's an intuitively appealing idea, we could expand our window. We could instead expand our window of opportunity and say, well, let me not average over outcomes for x being exactly 0.15, but just approximately 0.15. So, for example, suppose that I locate the individuals or observations which had an x between, say, 0.1 and 0.2, and I averaged over the outcomes for such observations. And I called that my estimate of the conditional mean of y at conditional on x being 0.15. That is, I form a local average. This seems like a good idea, or at least intuitively a good idea. Of course, suppose now that I was given not just 100 data points, but in fact 300. Now looking at our picture here, this window of opportunity between 0.1 and 0.2 seems a bit excessive. That is, we now have a lot of data points to average over, and we may want to consider a smaller window of opportunity. So this picture goes towards the point of stating that our idea of what's local is relative to the size of our data set. So here I've added 2 additional bars to show that, well, we might be willing to consider a smaller window of opportunity, as indicated here between the green and red vertical lines. That is, more data allows for a narrower window or a smaller window of opportunity. This idea is not specific to sample sizes of 100 and 300. If I were to jack up the sample size to 1,000, I may be willing to use an even smaller window of opportunity, and so forth and so on. So this illustrates that as the sample size increases, I might be willing to use a smaller and smaller window of opportunity in an attempt to pin down this conditional mean at a particular point. And, at least intuitively, this idea of using a small but vanishing window of opportunity should work well, provided that our target of observation is smooth. But I'll get back to that in a minute. So having introduced these ideas in an intuitive manner, let's proceed with a formal definition of the kernel estimator. So throughout, we'll consider a random sample, and for now we'll look at the case where both our inputs and outputs are scalars. Our target of estimation, or our estimate, again, is the function defined as the conditional mean of y given x as we vary the conditioning argument. But suppose for now that we're interested in estimating this function at a particular point, say x0. Now, in order to arrive at our window of opportunity, let's introduce a bandwidth, typically denoted by h. So h is some positive number, which you should think of as being small. Then we can create a window, or a ball, if you will, around our point of interest, x0, and of radius equal to our bandwidth, h. So this is our window of opportunity from our earlier slide when x0 was 0.15 and h, our bandwidth, was 0.05. Having defined this window of opportunity, that is, we've decided on x0 and h, we could identify or locate the relevant observations. That is, the eyes for which the regressor, in this case x, falls within our window of opportunity. Let's call that this calligraphic eye. Now, if we use this hashtag notation to denote the number of elements in a set, then we can write down the number of observations falling within this bandwidth window as hashtag I. Now, based on our definition of the window of opportunity, it amounts to just going through every single observation and counting whether x falls within h of x0. So here I've introduced this 1 as short for the indicator function. That is the function which takes the value of 1 if a, whatever we put inside, is true, and 0 otherwise. Having introduced this notation for our I set, as well as the cardinality of this set, the number of elements in the set, we can define the kernel estimator as the average of outcomes for observations which fall inside our window of opportunity. That is, this is just the average among eyes within our window. Now, if we plug in our definitions for I, as well as its cardinality, we see that the kernel estimator, this g hat of x0, is really just a ratio of two sums, which makes it appealing in that it is very simple to code this ratio. So when will this idea for estimating a conditional mean at a point work well? That is, what are the key conditions for kernel estimation? Intuitively, kernel estimation hinges on two conditions. Well, both intuitively and formally it hinges on, well, roughly two conditions. Intuitively, when we are expanding our window of opportunity from being at the point of interest x0 to points close to x0, we're stating that the means of such outcomes should be similar to the mean at our point of interest. Also, since we're using a local average, we should have points to work with, so the number of observations, that is the number of xi's that are close to our point of interest, should be sufficiently large, as otherwise there's no hope that the law of large numbers kicks in. Formally, what we need here is that the function, this was our g from before, the function given by the conditional mean of y given x should be continuous, or at least continuous at our point of interest. And towards the second intuitive condition, what we need is that the density, thinking of x as a continuous random variable, the density of x should be bounded away from 0 around our point of interest. That is, this should be data to work with. All right. So recall here that we've defined g to be the conditional mean of y given x as we vary the conditioning argument. Now let's define a random variable, we might call it epsilon, as the difference between y and its conditional mean. Then by construction, this random variable will have conditional mean 0, right? So, having introduced this epsilon notation, we could express our outcome of interest as a function g of x plus some unobservable epsilon, which has conditional mean 0. And this shows that our estimation problem amounts to a nonparametric mean regression. So often, the setting that we're considering is referred to as nonparametric regression for short. So let's spend a couple of slides here developing a theoretical result for kernel estimation, going into a bit more detail about when this method works and why it works. And what we'll develop here specifically is known as a mean squared error bound, which will hopefully become more apparent in a second. So we're considering the setting of nonparametric regression, and we're interested in estimating the function g at a point, x0. Now suppose the following three conditions hold. Suppose that g, our conditional mean function, is not only continuous, but in fact Lipschitz continuous. What this means is that if we take 2 points, x1 and x2, then the difference in function values is at most the difference in inputs up to some constant x, up to some constant L, sometimes referred to as the Lipschitz coefficient. Or Lipschitz constant. That was the first condition, stating that g is not only continuous, but Lipschitz continuous. Suppose also that the PDF of x is bounded away from 0. That is, x has density everywhere. And in addition, epsilon are unobservable in our nonparametric regression model, has bounded conditional variance. That is, since it has conditional mean 0, what we're stating is that the conditional mean of the square of epsilon is a bounded random variable. Now, if these three conditions hold, then there exists, one may show that there exists a constant, let's call it c, such that our kernel estimator, g hat of x0, our kernel estimator of g at the point x0, satisfies the following mean squared error bound. That is, the square difference between our estimator and our estimand, both at a particular point x0, in expectation, this square difference is no more than a constant factor times 2 terms, times the sum of 2 terms. The first term being the square of the bandwidth, and the second being 1 over the product of the bandwidth and sample size. All right, let's just spend a moment digesting this result. So here I've repeated our mean squared error bound for the sake of convenience. And let's consider each of the right-hand side contributions in turn. Now ideally, this square difference in expectation, loosely, this is a measure of distance. Distance between what? Our estimator and our estimand. So we would like this distance between the two to be small. And what our mean squared error bound shows is that for this distance to be small, it suffices that both the square of the bandwidth is small and 1 over the product of the bandwidth and sample size is small. Now the presence of the square of the bandwidth in turn implies that we would like to set h, the bandwidth, to be a small number. This goes back to our earlier intuitive condition that the means should be similar locally to our point of interest. And this idea goes towards having a small bias in estimation. On the other hand, the presence of this 1 over hn means that in order to make, we would like to set that term small, or make that term small, which in turn means that we'd like to ensure that the product of h and n is a large number. Now n is our total sample size, and h is the radius in our window of opportunity. So loosely speaking, hn is our effective sample size. And what this condition that hn should be large means that our effective sample size should be large. Now this goes towards ensuring that the variance in estimation is small. So these two conflicting, these two contributions pulls h in different directions. And these reflect the fundamental trade-off between bias and variance in estimation. So, continuing with our mean squared error bound, having discussed the meaning of the various components and what we would like them to be, let's look at a corollary stemming from this mean squared error bound. Now suppose that in addition to the conditions of the theorem, that the bandwidth h is in fact a function of the sample size, which satisfies the following conditions. As the sample size grows without bound, the bandwidth, a positive number, which now should be viewed as a sequence of positive numbers indexed by n, this sequence vanishes asymptotically. That is, it goes towards 0. But it goes towards 0 at a slow enough rate such that the effective sample size, the product of h and n, grows without bound. If our bandwidth or sequence of bandwidths is chosen in such a way, then one may show that the right-hand side here in our mean squared error bound goes to 0, and as a result, our kernel estimator at the point x0 is consistent for the conditional mean g at the point x0. But the mean squared error bound in fact shows a whole lot more, since it tells us exactly the rate at which this expression goes towards 0. So what one may deduce that not only does the kernel estimator converge towards our estimate in a probabilistic sense, but it does so at a rate equal to whichever of the two terms is slowest, which for now, or which at this point means that it goes towards 0 in probability at the rate of whatever is the largest of the bandwidth and 1 over the square root of the effective sample size. Well, with this observation in mind, we could think about using our mean squared error bound in order to determine the optimal rate. And this rate would balance the two contributions from our mean squared error bound. So the optimal rate arises from choosing our bandwidth, h, in such a way that the square of the bandwidth, and 1 over the effective sample size goes to 0 at an equal pace. And if one chooses the bandwidth in exactly such a way, then the kernel estimate may be shown to converge in probability to our estimate at a rate equal to 1 over cubic root of the sample size. That is n to the minus 1/3. Now typically, typical convergence rate for a parametric estimation method is 1 over the square root of the sample size, or n to the minus 1/2. So what we see here is that the kernel estimator in general experiences slower than usual convergence. Now, this feature is in fact a typical feature of nonparametric estimation methods. That is, nonparametric methods generally leads to slower rates of convergence than the typical square root n type of convergence. But more on this later on. All right. So thus far, we've introduced the kernel estimator as a local average, where we've used this window of opportunity to pin down or to express our idea of what's local and what's not. Note here that the use of these indicator functions, these indicator functions, they simply single out which observations are relevant and which are not. And then they discard the ones that are not relevant and attach the same weight, namely 1, to the observations which fall inside our window of opportunity. While this may seem intuitive, it doesn't really use any information besides observations falling inside the window of opportunity. More generally, one may find it desirable to let the weight use depend on the proximity to our point of interest in a more smooth manner, in a non-binary manner, for example. And one may do that by replacing the indicator function by some function, let's call it capital K, where the capital K is for kernel. Now, on picking these kernel functions to satisfy certain criteria, we've introduced a new type of estimator, which is often referred to as the Nadaraya-Watson kernel estimator. In fact, we've introduced a family of estimators depending on the K that we make use of. Now, a kernel function is simply a weighting function. And one may think of it as a PDF, although it need not be a PDF. Now, typically, while there are many good choices for weighting functions, the following three are representative of the spectrum of weighting functions. Initially, we considered a binary weighting function, which attached 1 to observations within the window of opportunity and 0 otherwise. And this idea we may think of, or these binary weights arise from what we may think of as a rectangular weighting function. Now this is simply function k of t, using the indicator that t is within 1 of 0. And here I've multiplied it by 1/2 in order to make the area under the graph integrate to 1. But that's not too crucial. Now this idea, or this type of weight, the rectangular type of weight, again, only uses the information that we are within the window of opportunity, but not any notion of proximity. An alternative kernel or weight function is the triangular weighting function, which uses a linearly declining, or attaches a linearly declining weight to the observations within our window of opportunity. That is, the weight declines linearly as a function of the distance to our point of interest up to a certain extent, where it is then set to 0 henceforth. Now both of these two previous weighting functions, the rectangular and triangular kernels, have a bounded window of opportunity, but one may also consider weighting functions which have an unbounded window of opportunity. For example, if we use as our kernel the density of a standard normal, this is a PDF of a standard normal random variable, then we are actually attaching positive weight to all observations. But again, this weight is declining in the distance from our point of interest. Okay, so these were somewhat representable of the kernels available, but there are many more out there. So thus far, we've only treated the scalar case, that is the case where both x and y were scalar random variables. However, typically one is interested in conditioning on not only a scalar random variable x, but in fact multiple conditioning variables. That is, we're also interested in the vector x case. So now let's expand our horizon and allow x to be d-dimensional, where d could be possibly larger than 1. We'll continue working with this kernel function as a univariate function. And since we're now in a vector case, our point of interest has to be vector as well, so that boldface x0 denote this point. Now when we're in a multivariate setting, there are many possible ways of extending the Nadaraya-Watson kernel estimation method, estimation technique, to a multivariate setting, but they roughly fall into these two choices. One states that we'll simply calculate the weights to be used by applying the kernel function coordinate by coordinate, and then constructing our total weight at a point, or observation I, as the product of the coordinate weights. This is often referred to as using a product kernel. A different way of constructing the weights is to first calculate the distance or proximity to the point of interest, and then calculate the weight as the kernel evaluated at this proximity when inflated by the bandwidth. Now both of these ideas can work in practice, and none necessarily dominates the other. So both of these are valid. Now for the purpose of implementation, let's consider the second method. So here I've provided a very basic code snippet to be used for a Python implementation. I suppose that we've already read in data on an outcome y, as well as a possibly vector or possibly matrix of regression or conditioning variables. So this x here could be n by d. Suppose that we've also already specified a point of interest, which here is just denoted by lowercase x, as well as a bandwidth value that we'll get back to later on. Then what's going on here is that we are calculating the vector of distances from our point of interest. That is one for each observation I, and then deflating by the bandwidth. Then we may take the resulting vector of proximities or distances, if you will, and evaluate and calculate the weights using some choice of kernel. So here I've made use of a triangular kernel, where we first single out the observations which fall within our window of opportunity, and then apply attach a weight which is linearly declining in the distance to our point of interest. The resulting kernel estimate, g hat, or this would be g hat at the point x, is then simply the ratio of sums, where we've weighted each outcome by the resulting kernel weights and divided by the total sum of weights. So this code snippet here you may take and make use of in constructing the kernel estimate at a particular point x. Now if you wanted an estimate of the entire function, if you wanted a kernel estimate as an entire function of this point, we could think about constructing a grid of x's, various points of interest, using the snippet as the meat entering a loop over the grid, and then interpolating between the results to get a function estimate. So that's what I've done in the next couple of slides. But first, let me introduce the setting. So here I'm considering a setting with simulated data. So I have an outcome y of interest and just a scalar regressor for simplicity. And we're interested in estimating the function g, the conditional mean of y, as a function of x. In our particular setting here, this function is a sine curve, which is not that economically relevant, but it makes for nice plots. And here, again, the particular simulation design is not that important, but x has support equal to 0 to 2 pi. That's just to make sure that we would be able to trace out the entire sine wave. Right, so here I've simulated data on y and x and scattered the points, but specifically here I've simulated 100 data points. So this is what you would see when opening your data set and creating a scatter plot. Applying our code snippet to a grid of points, we can, and then interpolating the results, we get a function estimate, this blue line here. So this is our estimate of the kernel, or this is our kernel estimate of the underlying function g. Now, since we're in control of the data generating process here, I can actually add on the graph for the true function g in order to assess the performance of the kernel estimate. So that's what we're doing here in the right-hand side panel. And what we see is that the kernel estimate in this particular setting with this particular sample size as well as bandwidth does fairly well in that it correctly captures the movements of the underlying G function, at least up to some sampling error, right? So, what about consistency? Is there any sort of convergence going on as promised by the theory? So here on the left-hand side, I'm just repeating the previous plot. And in order to illustrate convergence or not, on the right-hand side, I'm jacking up the sample size from the previous 100 to 400. So the right-hand side blue graph curve here is the kernel estimate arising from using now 400 points. And what we see is that while the estimate isn't necessarily closer at every single value of x, the distance between the two functions, as measured by the gap between their graphs, is vanishing. So this picture is indicative of some convergence taking place. Now notice here that towards the endpoints, that is towards the ends of the support of x, the kernel estimate tends to either overshoot or undershoot. This is actually a mechanical feature of the kernel estimation idea, in that in constructing a local average, we cannot average over values outside of the support. So if our estimate, our G function, varies or has curvature towards the end of the support points, it'll be hard to capture. And this is somewhat of a drawback from using the Nonparametric estimation technique. And for that reason, we'll look at a variant of the kernel estimation idea, which addresses this issue. So that's precisely what we're going to do now, where we'll consider the idea of local linear estimation. All right, so where does this idea come from? So going back to our setting with a scalar regressor, one may show that our kernel estimator, or Nonparametric estimator, can be expressed as the unique solution to a minimization problem, where what we're minimizing is the sum of least squares weighted by the kernel contributions, and where we're fitting a constant function, that we are fitting a constant function to our outcomes at each point x0. So the kernel estimator, or Nonparametric estimator, actually arises as the solution to a weighted least squares problem, where we're fitting a constant function. Now one may ask, well, why would we fit a constant function when we could also fit, say, a polynomial of some sort? And for example, we could fit a linear function instead. So now let's look at the resulting minimization problem, where instead of just using a constant, we've also added a term which is linear in the difference between regressors and our point of interest, but is otherwise the same expression. Now, the solution to this problem gives rise to what's known as the local linear estimator, where the name comes from this linear term, as well as estimation being local in the sense of being at a point. Now the local linear estimation method is in some sense desirable in that it not only provides an estimate of the function at a point, but also its derivative at a point. And one may, similar to the Nonparametric setting, one may create a multivariate extension thereof. And I highly encourage you guys to write it down in order to make sure that you understand the steps necessary. But continuing with our scalar setting, let's look at how one may implement the local linear estimator. Now, I could write this in Python, but I think it's instructive to just look at the math to see how it's, in fact, very simple to implement. So what one could do here is to take our original outcomes after having calculated the kernel contributions. We'd multiply the original outcomes by the square root of these kernel contributions. And think of this as an artificial outcome, say y tilde. Similarly, we could take our original regressors, which would be, say, 1 and x, and similarly scale them by the square root of the kernel contributions, having centered the x's at our point of interest. Now call the resulting artificial regressors x tilde. Then local linear estimation arises from using ordinary least squares on these transformed outcomes, on the transformed regressors. And here I've just repeated the formula, or stated the formula for ordinary least squares for convenience. Now the solution to this least squares problem, let's call it gamma hat, which is a 2×1 vector. From this solution, we could extract the first element, and that would be our local linear kernel estimate. We could also extract the second component, and that would be an estimate of the derivative of g at the same point, x0. Now, up to this point, we've talked about implementation as if the bandwidth h was given. But I think it's an important point to make here is that one needs to choose the bandwidth in order to implement these methods in practice. And more generally, every nonparametric estimation methods involves some sort of tuning parameters, some sort of bandwidth or something pinning down a window of opportunity in a general sense in order to implement the method. So while there are many approaches to determining these tuning parameters, here when we're talking about bandwidth selection in a regression context, a natural way to proceed is to determine the amount of tuning by using what's known as cross-validation, or specifically here, leave one out cross-validation. So what is that? Let's just for the moment think of us wanting to implement the Nonparametric estimator. So we're searching just for a value to use, a value for the bandwidth h to use for the Nonparametric estimator. Now, let's use the following notation, where we let g hat with a superscript -i and a subscript h denote the kernel estimator of g, following the exact same formula as for the Nonparametric estimator, using a bandwidth h, but only all but the ith observation. So we're dropping the ith observation from our sums. Then, for each candidate bandwidth, each h, we could go through our... Now, let me start over by saying, if we take these leave one out kernel estimates and evaluate them at the x corresponding to the left out observation, then we get a prediction for the outcome for that observation. So we could think about doing this for each observation in turn and creating these out of estimation sample predictions. Then we could calculate the squared difference between the actual outcome and our prediction thereof and add them up, or in this case, average them. Now, here we've averaged out we've summed out the I subscripts and superscripts. So what's left here is a function of the bandwidth. And since this expression here is a is a measure of prediction error, it seems, at least intuitively, it seems like a good idea to minimize this expression, or to choose a bandwidth which minimizes this expression. So that's what we'll do. We'll minimize this measure of prediction error or misfit and choose our bandwidth from a collection of candidate bandwidths such that we minimize the out of sample prediction error. This choice, since we've left out each observation in turn, is often referred to as the leave one out choice of the bandwidth, or leave one out cross-validated choice of the bandwidth. Now, here I chose the Nadaraya-Watson kernel estimator for simplicity, but the exact same procedure actually applies if we were to use the local linear estimation method. And we could similarly think about applying this method in a multivariate case, that is where x is a vector. So these assumptions of a scalar x and the Nadaraya-Watson estimator were only made for simplicity. Finally, let's talk about an issue often referred to as the curse of dimensionality. And for this purpose, let's return to the setting where x is actually allowed to be vector. So now x is allowed to be d by 1. So suppose for simplicity that x is in fact uniformly distributed on the unit cube, where this is a cube in Rd. And suppose also, again for simplicity, that we use the Nadaraya-Watson kernel estimator with a rectangular kernel. And we use a product form for the kernel. Then our kernel estimate takes this form. Now, based on this formula, we see that the kernel estimate at the point x0 is just the average of outcomes corresponding to the regressors which fall within a cube centered at x0, and with diameter given by 2h. Using our assumption that h was uniformly distributed, we could actually calculate the expected value, or the expected number of observations falling within this cube. And what we get, due to the uniformity, is that this expected number of observations is given by the sample size times the diameter to the power of d. So let's play around with this expression. And suppose for simplicity that the bandwidth is 0.05, that is a 20th. And therefore the diameter of this cube is a tenth. Now suppose that our sample size was 1,000, which is large but not overwhelmingly large. Then in one dimension, our previous expression states that, well, on average, our kernel estimate arises from an average over n being 1,000 times 2 times 0.05, 2 times the bandwidth, which in this case is 100 observations. So our local average is, on average, 100, based on 100 observations. The same calculation in 2 dimensions yields that, on average, the kernel estimator is based on an average of 10 observations. And in moving into space, 3 dimensions, the average here of using 1,000 observations and a bandwidth of a 20th narrows it down to just, on average, we're using a single observation. So clearly this procedure has challenges. So a general statement here is that as the dimension, that is the length of the conditioning variable d, increases, estimation using kernel methods rapidly becomes difficult. Right? We quickly run into trouble. And we see here, based on these heuristic calculations, that even in reasonably large samples, say where sample size is in the tens of thousands or even millions, nonparametric estimation here, it's really only feasible with at most 3 to 4 continuous right-hand side variables. Now, this, while our previous calculation here was for the Nadaraya-Watson kernel estimator, and it was based on a particular assumption about the regressors X, one may show that this statement here holds quite generally. That is, we could apply the same comment to nonparametric estimation methods beyond the kernel universe. So, while nonparametric approaches have this intuitive appeal of not being dependent on particular functional form assumptions, there are limits to their usefulness. So this illustrates what's known as the curse of dimensionality. That is, the dimension of the conditioning variable inherently puts a limit on the usefulness of the method. So this concludes our discussion of nonparametric methods.